Why don't we share? I guess it's an indication of how useful my lectures are. Sure. I'm not offended. I don't want to be around me either. Okay, well, in any case, we will get started. So what we've been working on recently, or let's say last time, is we were trying to come up with a derivation of the Gaussian distribution. And we were going to try to get there by starting with the binomial distribution, because we know the binomial distribution well now, and we derived that from first principles. And so if we can make some manipulations and get a new type of probability distribution, that would be one useful way of doing it. So the question was, let's start with a binomial distribution, thinking about this random walk problem where we could step left or right. And we were going to ask, what is the probability of taking m extra steps to the right when the probability of any individual step being left or right is 1/2? Okay, and so we were going to take x steps to the right, which we were going to define to be half the total steps plus half of the number of extra steps. And then the number of steps to the left would be n minus x, which would be half the total steps minus half of the extra steps to the right. And what we're trying to do is, believe it or not, we're going to try to recover this kind of result. And the way we were going to do it is we were just going to write down the binomial distribution where for x, we use n/2 plus m/2. And for n minus x, we use n/2 minus m/2. And then the binomial distribution also has like this p raised to the power x times 1 minus p raised to the n minus x. But we're going to take p to be 1/2. And so those two things combined to be 1/2 to the power n, or 2 to the minus n. So that's where that factor comes from. So we had written down this binomial distribution. We did one cancellation, and sort of this is where we were left at. In order to get here, remember we used, notice there's no factorials in this expression, and the binomial distribution is full of factorials. So what we ended up doing is we ended up using the Stirling's approximation for factorials of large numbers. And that's what brought us here. And so we're going to do some more little manipulations here, and we should be able to get this done today. Okay, so the first thing we're going to do is we're going to notice that we have these two little square root factors. And so what we could do is we could combine these little square root factors. Okay, so let's just do that. If I multiply these two square root factors together, we'd have n over 2 plus m over 2 times the square root of n over 2 minus m over 2. That's the same thing as, well, it's still in a square root, so we'll still have our square root. But we're going to get n over 2 squared. And how do I want to write it? I'll write it as n squared over 4. We're going to get minus m squared over 4. And then the cross terms would cancel because we'd get a minus n times m, and then we'd get a plus n times n. So those cross terms factor out or cancel out. Okay. So if we do that, then our probability is going to be, so we have an n to the power n, we still have a square root n, and we still have 2 to the minus n. So that's all the same in the numerator. We have a root 2 times pi. So we have 2 times pi under a square root. So I'm going to put that over here. Okay. And then I'll put in this square root factor that we just worked on. So it's going to be the square root of n squared over 4 minus m squared over 4. And then let's see, what else do we have? We have these two factors, and what am I going to do with them? So I am going to say that, okay, let's do this. Let's do n over 2 plus m over 2 to the n over 2 plus m over 2 times n over 2 minus m over 2, n over 2 minus m over 2. Okay, so what can we do with this? So if I have a power that has a sum in it, I can write that as a product of powers. So we could write this as n over 2 plus m over 2, n over 2, and then I'll do the n over 2 minus m over 2, n over 2, and then we could have n over 2 plus m over 2, m over 2, and then n over 2 plus m over 2 minus m over 2. So there's the difference. We got a minus sign in the second factor. And what have I done wrong? No, that's correct. I think that is correct. Okay.
A negative in the last factor there.
Yeah, I should have, one of these should have a negative, shouldn't it? That one right there. Is that what you're talking about? Yes, you're right. Thank you. Good. Perfect. Okay. So these ones can be combined like we did before. Minus m squared over 4. And this is all to the n over 2 power. And then these ones, we can't combine them because it's not the same power, but we could write this in a different way. We could say, look, this is n over 2 plus m over 2 divided by n over 2 minus m over 2, all raised to the m over 2. That works because I've put this in the denominator, which takes care of this minus sign. Okay, and then we could cancel all those 1/2 factors. All right, so if we put those results in, then we end up over here. Let's call this 1 and 2. So part 1, we'll just stick over here. And then we have an n plus m over n minus m to the m over 2. Okay, good. So I think that all makes sense. We haven't made any more approximations yet beyond the Stirling's approximation that we did last time. Okay, good. So let's consider then this n plus m over n minus m to the m over 2. So what I'm going to do is I'm going to pull out an n from the numerator and the denominator. Okay, and so that would be 1 plus m over 2, 1 minus m over 2 to the m over 2 power. Okay, and so that is equal to 1 plus m over, sorry, why did I put 2? Sorry, I'm being silly. I factored out an n, right? So there's an n, and here is 2. Okay, so we have one of these in the numerator and one in the denominator. So it's 1 plus m over n times 1 minus m over n raised to the minus 1, and then all of that raised to the m over 2. So now this is the time when we're going to make our first next approximation. And remember, what we imagine doing is taking a small number of extra steps to the right compared to the total number of steps. So this ratio m over n is a small number. So note that m over n, I keep writing 2, m over n is small if we imagine a small number of extra steps to the right. Okay, so 1 minus m over n to the minus 1 is approximately, so what's the approximation for 1 minus a small number raised to some power? Does anyone remember? Yeah, you're right. I could just ignore this completely and just get a 1. That's absolutely true. What if I wanted to do a slightly better approximation, but closer to reality? Do you remember 1 plus x to the power p is approximately 1 plus px for the absolute value of x much less than 1? This is the binomial approximation. This, for what it's worth, is my favorite approximation because it appears so often. Like this physics is kind of a funny thing in that most problems are really hard to solve. And so what we end up doing is trying to solve problems in certain limits where you think of some quantity being small or some quantity being large compared to others. And so this appears frequently because we make the assumption that x is small compared to the 1, and then you could write this power as this linear equation, which makes problems easier to solve. So our power is minus 1. So we'd have like a minus 1 here. Oh, internet connection. Okay, so 1 plus minus 1 here. So anyways, our power is negative. Our value of x is negative. So those negative signs cancel. And so this thing is just approximately 1 plus m over n. And I did it again. And okay. So that means then if we make that approximation, what we have is 1 plus m over n. And then we made this approximation for the second factor. It's in fact just 1 plus m over n again. And this is all to the m over 2. And what I'm going to do is I'm going to multiply out these factors inside the square brackets. So it's 1 plus 2m over n plus m over n squared, all to the m over 2. Okay. If m over n is small, which it must be because we just made this approximation, then m over n squared is really small, right? So suppose this is, 10 to the minus 3, then this one's 10 to the minus 6, right? So if m over n is small, then m over n squared is very small. And so this thing is going to be approximately, this time we're just going to drop this m over n squared factor because it's so much smaller than the two other terms that are inside the square brackets. And so it's going to end up being 1 plus 2m over n to the m over 2. All right. So we're going to make that substitution in our expression here for this probability. So I can't remember all of these factors. So I'm going to copy this thing and we'll make some edits. Oops. So therefore, our probability then is approximately, what did we work on? We worked on this thing right here. So I'm going to erase that and replace it with, let's see, 1 plus 2m over n to the m over 2. Okay. So what do we have? We have n over 2 pi square root. So I'm going to combine the n and the 2 pi in the square roots there. Then we have, let's see, we have n over 2 to the power n. So I can combine these two things, put the 2 in the denominator, and then they're both to the power n. Okay, and then divide by. So let's see, we've taken care of the square root 2 pi. I'm going to factor out an n squared over 4, and I'm going to take it out of the square root. That's going to give me an n over 2, and then I'll have a square root of 1 minus. So when I factor out the 4, I'm going to take this one with it, but now I'm going to get minus m over n squared. Okay. Then from here, I'm going to do the same thing. I'm going to factor out the n squared over 4. So we're going to get, let's see, n squared over, oh, sorry. What do I have to do? N squared over 4. That's going to be to the power n over 2. And then what's left? Oh, I'm going to run out of space, aren't I? Let's move some of this over. Okay, so we're going to get 1 minus. I took out the 4 here, so that's already gone. So we have an m squared divided by n. And that's all to the power, what, n over 2? Okay, so far so good. And then this one we'll just write down again. So it's 1 plus 2m over n. And that's all to the m over 2. All right, good. Now, let's see what we have here. What's n squared over 4 to the n over 2? What can I do with this 1 over 2 here? It's a square root, right? So this n squared becomes n. The 4 becomes 2. We'd have n over 2 to the power n over 2 to the power n. So, yeah.
Two things. One,
yeah.
If we have m over n again here, can we say that that's really small and cancel it out because we've got 4?
This one here?
Yeah.
Yeah, we may end up doing that. I'm not sure. Let's see. Yeah, let's see what we're going to do here. Yeah, we are going to use an approximation again. So, okay. And the other thing was what?
Earlier when we did the approximation, we got that like the two terms is the same, like 1 plus m over n. Why would we not just combine those to get a square and we can cancel out the square with the square root?
So you could, I see, square it here and then cancel the square root. Yes. So let's see what would happen if we did that. Let's
what? So it would be less approximation.
Yeah, let's see. So what I think you're suggesting, let's see what happens if we take this, copy it. Here, let's just go over here. Okay, so what I think you're saying is this should be equal to 1 plus m over n to the power m, right?
Is that number 2?
Yeah, that's right, like this. Right, and then if we did now the small approximate, so this would be approximately 1 plus m over n, which is 1 plus m squared over n, which is, I guess, a little different than what we ended up getting, right? So we ended up getting this thing. Sorry.
1 plus 2.
1 plus. Oh, yeah, you know what? That's going to lead to a similar kind of thing because I could do here, I could do 1 plus m over 2, 2m over n, and then cancel out. And so we get the same sort of thing. Yeah, yeah. So I think then you are correct. That's another path to a similar result. Yeah, good, good. Okay, good. So then what do we have here? We have our probability of m extra steps to the right is approximately. Okay, so we're going to get a 2 from this n over 2. So we get a 2, and then I have a square root 2 pi. Then let's see, we have a root n divided by n. And so that's going to be 1 over root n. All right, so we dealt with these things, that thing's canceled. And so we just have now these 3 factors in the denominator. And I'm going to write this as 1 minus m squared over n squared to the minus 1/2 is the square root. And then I'm just going to put this to the minus n over 2 and this to the minus m over 2. And so those are going to be the same. So 1 minus m squared over n squared minus n over 2, 1 plus 2m over n to the minus m over 2. All right. So the next thing we're going to do is we're going to take the natural logarithm of this whole expression, and then we're going to apply an approximation. So now we're going to take the ln of this probability, and we're going to use, I think we used this approximation last time, the ln of 1 plus x is approximately x when the absolute value of x is small. So you were asking about, like, are all these things still small? And yes, they are still small, and we're still going to do an approximation. Okay, so the ln of the probability is approximately, okay, so we're going to have the ln of 2 over root 2 pi. Then I'm going to get the ln of 1 over the square root of n, or it's the ln of n to the minus 1/2, which is the same as minus 1/2 ln n. So we'll have a minus 1/2 ln n plus, let's see, we'll get the ln of this thing is going to be a minus 1/2. So it'll be minus 1/2 ln of 1 minus m squared over n squared. Then we would get minus n over 2, the ln of 1 minus m squared over n squared, minus m over 2, the ln of 1 plus 2m over n. All right, good. So when we use this ln approximation, everything in here is just going to be minus m squared over n squared. So it's going to be minus m squared over n squared. Over here is the exact same thing. In fact, I need to include the ln in there. This is minus m squared over n squared. And then this one is going to be what? This is going to be 2m over n. Okay, and so let's see what this all boils down to. So the ln of our probability is approximately ln of 2 over root 2 pi. That hasn't changed. Okay, then it's minus 1/2 ln n. That doesn't change. So now things are going to be different. So let's see, minus 1/2 and then the minus cancel. So we're going to get m squared divided by n squared with a 1/2. So I think it's plus 1/2 m squared divided by n squared. Okay, then it's going to be plus 1/2. And then we have an n divided by n squared. So it's going to be plus 1/2. It should be m squared over n. Let me know if I make a mistake. And then this 1/2 and this 2 are going to cancel. And we're going to get m times m is going to be an m squared over n. This is just a minus sign. So we should end up with a minus m squared over n. Okay, good. I think that might be right. So the first thing we could notice is that we have m squared in 3 of the terms. In one of them, we divide by n squared, and in the other 2, we divide by n. N is a large number, so this is small compared to these 2 terms, and we're going to neglect them. That's probably essentially, you were probably just going to make that approximation earlier, but I think that's essentially what we're doing now. Okay, so this one is small compared to m squared over n, and so we will ignore it. The last 2 terms can be combined, right? So they're the same, they just have opposite sign and one has a 1/2. So the last 2 terms combine to be minus 1/2 m squared over n. All right, so then our probability, we're getting close actually. The ln of p is going to be approximately the ln of 2 over root 2 pi minus 1/2 ln n. And then we ignore that the third last term and we combine the last 2, minus 1/2 m squared over n. I think. Okay, good. So in fact, to simplify this even further, I know I wrote this. This used to be like the square root of n, the ln of 1 over the square root of n. What I'm going to do is I'm going to combine these two, right? Combine the lns. I think what this should be is ln of 2 over root 2 pi, and I'll write it like this, root n. Okay. And then it's minus m squared over 2n. All right. So finally, what we'll do now is we're trying to get this Gaussian distribution. We want this to look like a Gaussian distribution. So now we've taken the ln of the thing. Let's take the exponential. So we get rid of the ln. So we now exponentiate so that p m over n is approximately equal to, so it's the exponential of ln of all of the stuff, 2 pi root n, and then it's exponential of minus m squared over 2n, which is equal to 2 over root 2 pi root n e to the minus m squared over 2n. So this is actually starting to look a little bit like what we wanted to get. It's not, maybe not quite there yet, but we have an e to the minus something squared, and then we've got a prefactor that involves like a 1 over root 2 pi. Let me just show you what we were trying to obtain. We're trying to obtain this thing. And so we have the 1 over root 2 pi. We have e to the minus something squared. It doesn't quite look like this yet, but the other thing we should remember is that mu is n over 2, and sigma is root n over 2. So mu is n over 2, sigma is root n over 2. So recall that mu was equal to n over 2, and sigma was root n over 2. And we have a root n and a 2 here. So this 2 over root n is 1 over sigma. Okay, so Pmn is equal then to 1 over root 2 pi times sigma. And then I won't do anything to the exponential yet. We're going to still work on that, like so. Okay. So m is the number of extra steps to the right. How are we doing time-wise? Oh, good. We still got tons of time. Okay. So recall that x was the number of steps to the right was given by this expression. So half the steps are to the right, and then there's some extra ones. So if we solve for m, we would multiply by 2 and then subtract the n. So we could write m is equal to 2x minus n. Okay. So our probability is then going to be equal to 1 over root 2 pi sigma. So that's all good. E to the, all right, what are we going to end up with? M squared. So it's going to be minus 2x minus n squared divided by 2n. Okay. I'm going to pull this 2 out of the square. So when I pull it out, it'll become a 4. So it's going to be minus 4. And then it's x minus n over 2. It's still everything divided by 2n. Okay. Why would I do that? It's because now we have this n over 2 here, and that's the same as the mean. So this thing here is mu. And so our probability is equal to 1 over the square root 2 pi sigma e to the minus. I'll do it this way. Let's do x minus mu divide by, let's see, we have a 2, and I'm going to do n over 4. Okay, so I take the 4 in the numerator, and I put a 1 over 4 in the denominator. But this n over 4, if I square sigma, that's n over 4. So this thing is sigma squared. I'm missing a square. Is that what you're going to say?
Yeah.
Yep. Yeah, you're exactly right. And I'm missing it here too. Is that right? Yes. Good. Perfect. All right. So finally then, this has been a long derivation with lots of approximations, but I wanted us to see where this Gaussian distribution comes from and its relationship to the binomial distribution. So we end up with a 1 over root 2 pi sigma e to the minus. So we have a x minus mu. That's all going to be squared. I also have a sigma squared here. So I can put that in here and squared. And I still just am missing my 1/2 factor. And so there it is. And this is the Gaussian distribution. And essentially, for basically the rest of the term, all of our results are going to basically be derived assuming Gaussian distribution. And a Gaussian distribution assumes that it's going to be symmetric about the mean. And really what that means is if you make a measurement, it's just as likely to fall below the mean as it is above the mean. And so that means your errors in your measurements are completely random. So you have a kind of like the most likely value, and then it spreads out symmetrically on either side of that. Okay, good. So that's our Gaussian distribution. Let's look at some of the properties of the Gaussian distribution. Okay, so if you were to plot this function, like I said, it's going to be symmetric. And so we'll plot our Gaussian distribution on the vertical axis. The horizontal axis, I will put x minus mu is our horizontal axis. Okay, so if I put x minus mu equal to 0, then I have e to the 0, which is 1. And because that's a negative exponential, 1 is as big as it could ever be. Because I'm always going to have minus 1/2 times something squared. And that something squared is always going to be a positive quantity. So the biggest I could make this exponential factor is a 1. And that occurs when x minus mu is equal to 0. And so if that's over here, that's where our peak is going to be. And if you plot the function, you know, it'll look something like this. It's supposed to be symmetric. So any asymmetries that I've drawn are unintentional. Something like that. Okay, so over here is approximately sigma, over here is approximately 2 sigma, and over here is approximately minus sigma, and over here is approximately minus 2 sigma. So properties, what are the properties? The total area is 1. And so that means if I was to take the integral of the Gaussian distribution from, let's say, x equals minus infinity to x equals plus infinity, that would come out to be 1. And so then I can ask questions like, what is the probability that I measure some quantity between x and x plus delta x, for example? Well, it's just the corresponding area underneath that graph. So the probability of a measurement falling between x and x plus dx is, well, all you would do is you would find wherever that is on your graph, and you would say, okay, this is my value of x, or my x minus mu value. And then I just go up and we pick some width dx. And this is going to be PG at x. And that defines some area. If I take the height of that rectangle PG, times it by the width of that rectangle dx, that gives me the area, and that corresponds to the probability of a measurement landing between x and x plus dx. So here would be something like x, and then over here would be x plus dx. Okay, so it's just going to be that infinitesimal probability would be the probability distribution, or the Gaussian distribution, times the width of that interval. Okay, so this is only valid for an infinitesimal little dx, where I can approximate that rectangular, or that area, as being like a thin rectangle. If I want to know what is the probability of a measurement falling between some x1 and x2, where the distance between the two is not infinitesimal, then we just have to integrate. So we take all these little rectangles, put them one by one beside each other, add up all their areas, which is effectively just evaluating that integral. So the probability of measuring a value between, let's say, x1 and x2 is, so p x1 to x2 is going to be the integral of the Gaussian distribution, which is a function of x and is characterized by a mean and a standard deviation. And we're going to integrate from x1 to x2. Okay. And so let's just draw what that would look like. I'll draw it this time as a function of x. The Gaussian distribution is this kind of, oh, I'm not happy with that. Okay, something like that. And so we could pick some x1 value here and x2 value here. And the probability of a measurement falling between these two extremes is just given by the fraction of the area. So this might be like 80% of the area or something, which gives you an 80% probability. Okay. So let's see if we can actually work out this kind of integral for a specific example. So the example we'll do is find the probability of a measurement falling within delta x of the mean. Okay, so we want the probability of something falling within the mean minus some delta x, and the mean plus some delta x. And all we have to do is evaluate this integral. And we're going to go from mu minus delta x to mu plus delta x of the Gaussian probability distribution, which is 1 over root 2 pi times sigma. And then we have the exponential of minus 1/2 of x minus mu divided by sigma squared. And then I need my dx. Okay, now we're going to see that this integral is not easy to evaluate. In fact, I think you can only evaluate it numerically, but we can reformulate this to put it in a bit of a nicer form. And we're going to do that by making a substitution. So let's make a substitution. Z is going to be equal to x minus mu over sigma. So it's just the stuff that's inside the square of that exponential. So if I do that, then when x is equal to mu minus delta x, z is equal to what? So if I put in mu minus delta x, I'm going to have a mu minus mu will cancel. I'll just get a minus delta x over sigma. So minus delta x over sigma. And then when x is equal to mu plus delta x, we should just get z is equal to plus delta x over sigma, I think. Okay, and then if I take the differential of this thing, dz, mu is a constant. Its differential is just going to contribute 0. And so we get dx over sigma. So dx over sigma. And we just want to substitute these things in. So p mu minus delta x to mu plus delta x is equal to the integral. Okay, so it's going to be minus delta x over sigma to plus delta x over sigma. We're going to have 1 over root 2 pi sigma. That doesn't change. But now we're going to have the exponential of minus x minus mu over sigma is all z. That's our substitution. So we end up with a z squared. We still have the 1/2, so we'll put a z squared over 2. And then the dx is going to be sigma times dz. So we would have sigma dz. Okay, and then we could cancel a factor of sigma. Okay, so this is going to be 1 over root 2 pi integral from minus delta x over sigma to delta x over sigma of e to the minus z squared over 2 dz. And so that is the integral that we would have to evaluate. I do not think that you can evaluate this integral analytically. You may remember that if you were to set your limits to plus minus infinity, have you seen the Gaussian integral? So what is the integral of this thing if this is minus infinity to plus infinity?
Something to do with pi.
Yeah, it's just this square root 2 pi. Like it would have to be because that would essentially be asking, what is the probability that your measurement falls between plus minus infinity? And it has to be 1, right? And so this integral without this prefactor, if you could change the limits to plus minus infinity, that's going to be root 2 pi. And that is an exact integral that can be evaluated. But when the limits are not plus or minus infinity, then you need to evaluate this numerically, I believe. So we cannot evaluate analytically. This requires Numerical methods. Numerical methods. And so you could do this, you know, with Python or MATLAB or, I don't know, what do people like to use? What do you guys call it? Desmos or something? Numerical methods. Okay, but I'm going to make a little table and we'll put some of these results in. How are we doing? Oh, 2 minutes. That's lovely. Okay, delta x over sigma. So P of mu plus delta x to mu minus, minus delta x to plus delta x. So if we put in delta x over sigma is equal to 1, that's like saying delta x is sigma. So what's the probability of finding the result between mu minus sigma or mu plus sigma, or 1 standard deviation, within 1 standard deviation of the mean? Does anybody know? What does that probability work out to be? Yeah, it's like, it's 68%. Okay, and then what's the probability of finding a measurement that falls within 2 standard deviations of the mean? 95. And 3 standard deviations of the mean is like 997. I'm going to do a few more just to make a point. 4 and 5. So this is 0.99937. And then this is 0.1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, 6 nines and then a 4. So for a Gaussian distribution, they often talk about the 68, 95, 99.7 rule. And so that's just all it's there to tell you is that 68% of your measurements will fall within 1 standard deviation of the mean. 95% of them will be within 2 standard deviations, and 99.7% of them will be within 3 standard deviations. So often people, when they make a measurement and they find that their result is not within 1 standard deviation of the accepted value, and then sometimes people say, well, the experiment didn't work. Well, that's not really true, or it's not necessarily true, because 32% of the time, your result will be more than 1 standard deviation from the mean, okay? The other point that I wanted to make is, I don't know if you've ever heard of like particle physics announcing results, and they will say that, you know, we've discovered a new particle like the Higgs boson with 5 sigma certainty. And so what they're really saying is that the probability that what they've discovered is like a little fluctuation, like noise in the data, is 1 minus this number. And so it's a very small chance that the signal that they've uncovered is not actually due to whatever particle that they're looking for. And so in the history of particle physics, I don't know all the details. Maybe I'll look it up and talk about it Friday. But there was one particle where they announced the discovery, and maybe it was like with 3 sigma confidence, something like that. And so there's only a 0.003 chance that it was a fluctuation, and it turned out to be not a particle. So they announced a false discovery, and then I think it was a few years later, they discovered the same particle, but with a higher confidence interval. So when particle physicists tell you 5 sigma certainty, they're quite certain, okay? All right, good. So that's where we'll stop. Thank you very much. And we'll see some of you in the lab. All right, you're welcome, Samuel.